Hi guys, up to now we have studied about induction motor operation, in which we studied about the speed of various magnetic fields operating inside the induction motor. Then we studied about torque slip characteristics of induction motor, efficiency and various losses in the induction motor, and we have studied about starting, speed control and braking of induction motor. So when we studied about starting, the problem that we were trying to tackle was to reduce the starting current and increase starting torque. This can easily be done in case of wound rotor induction motor by introduction of external resistance and increasing the rotor resistance. But in case of squirrel cage induction motor, there is no provision of adding external resistance. So we have to try other methods to increase the starting torque. So we change the rotor design to increase the starting torque. So there are some special rotors that are studied in case of squirrel cage induction motor to increase the starting torque. So in this lecture we will see about the special rotor designs and some concepts of harmonics in case of induction motor, and we will see what effects do the harmonics produce inside the induction motor. So first let us study about rotor design. The first special type of rotor is defined as deep bar rotor. So this is the deep bar rotor. The rotor is narrow but it is deep. Here the rotor is wide but it is shallow. As the depth is increased, the distance of rotor bar from stator increases. The distance of this rotor bar from the stator increases. The farther the rotor from the stator, higher will be the leakage flux. Okay? Or we can say less flux will be linking between the rotor and the stator since the distance is high. So that is why if the leakage flux increases, phi is defined as L into I. So leakage inductance will also increase. So leakage reactance will also increase. Okay. So that is why the leakage reactance of 4 is greater than leakage reactance of 1. Now what happens when we start the motor? Slip is 1, so rotor frequency is equal to F. And we know the reactance is proportional to frequency. So the difference in the leakage reactance of 4 and 1 is more prominent at starting because the frequency of rotor is high. If the difference between these reactances is large, then the current will try to take the path of minimum resistance or minimum impedance. So current will be concentrated in rotor bar 1. If current is concentrated in rotor bar 1, that means most of the current flows through the 1. Now how to increase the starting torque using this property? What design do we use is, we increase the resistance of 1. Okay. Since current flows through 1, I1 is greater than I4, what we do is make R1 greater than R4. How to do that? Area of cross section of 1 will be less than area of cross section of 4. Okay. So that way resistance of rotor bar 1 will be higher as compared to rotor bar 4. So by that what will happen, since the current is flowing through a rotor bar 1 and it is facing a higher resistance. So effectively we have increased the rotor resistance. That is how we will increase the rotor torque, or we will increase the starting torque. Okay. But now as the speed builds up, as rotor speed builds up, slip will go down. As slip goes down, rotor frequency will decrease because it is equal to SF. That's why the difference between XL1 and XL4 will decrease. Okay. Both will try to become more and more uniform. So if the rotor bar's reactance is become equal, then current will get uniformly distributed between rotor bars 1 to 4. So current will spread now from 1 towards the 4. So it will be more uniformly distributed under the running condition. So effectively it faces a higher resistance during the starting, and during running conditions it will be uniformly distributed in the entire rotor bar. So that is the design of deep bar rotor. Another such design is double cage rotor. As shown here, there are two cages. Since we are talking about squirrel cage, this is your inner cage, this is outer cage. Again, since the inner cage will be farther from the stator, that means leakage flux of inner cage is greater than leakage flux of outer cage, due to which leakage reactance of inner cage is greater than leakage reactance of outer cage, due to which at the time of starting, current of outer cage is greater than current of inner cage at starting. So most of the current will flow through outer cage. So what we do again here, we will try to increase the resistance of outer cage by taking cross-sectional area of outer cage less than cross-sectional area of inner cage, so that resistance of outer cage is greater than resistance of inner cage. That way, effectively at the time of start, current will be concentrated to outer cage, but it will face a higher resistance. As it faces higher resistance, the torque will be higher because starting torque is directly proportional to the rotor resistance. Again, when the speed increases, the slip will decrease and the rotor frequency will go down. As the rotor frequency goes down, the difference in the leakage reactances goes down. Current gets uniformly distributed between the inner cage and the outer cage. The functionality is simple, same as deep bar rotor, but here instead of deep bar or multiple rotor bars, we have multiple cages which are connected in parallel. Remember, their connection is parallel. So if we see the torque slip characteristic, this indicates the torque due to the inner cage. Okay, this is the normally inner torque or inner cage. It is normal torque slip characteristic, but if you see the torque slip characteristics of outer cage, as the speed builds up, what will happen? Slip goes down, rotor frequency, which is equal to SF, it also decreases. If the rotor frequency decreases, then what will happen? The difference in the reactances X outer and X inner decreases. So current starts increasing in inner cage and current starts decreasing in outer cage. If current in the outer cage starts decreasing, torque is proportional to I square. It also goes down. That is why the torque of outer cage decreases as the speed builds up. Okay. So remember this point. As the speed builds up, the reactances become more uniform. So current will be transferred from outer cage towards the inner cage. As the current in outer cage goes down, the torque will also go down. The total torque will be sum of the two, and if you see, starting torque has now increased. So that is the effect of double cage rotor. Okay. So these are the ways by which we can increase the starting torque of a squirrel cage induction motor. Next term that we study is called as crawling. See, there are three types of harmonics in case of induction motor. First is 6n plus minus 1. These are called as belt harmonics. Okay, and these are space harmonics. Space harmonics means these are generated due to non-uniform flux distribution in space. Now if n is equal to 1, the harmonics that are produced are 7th, 6 plus 1, this is a positive sequence harmonic. Okay, 7th harmonic acts as positive sequence, and speed of 7th harmonic is ns by 7. That is, the rotating magnetic field produced by 7th harmonic has a speed of ns by 7. The speciality of belt harmonics is The synchronous speed of belt harmonics is synchronous speed divided by the order of harmonic. Why is it so? Because higher the order of harmonics, higher will be the frequency of current reversal. And as the current reverses, there will be pole created. And as I told you in pole changing technique, between two oppositely current carrying coil, always there is a pole. So if there are more frequent current reversals, more poles will be induced, and we know that synchronous speed is inversely proportional to number of poles. That is why it is ns by 7. Similarly, other harmonic will be fifth, 6 minus 1. It is a negative sequence harmonic. Speed will be ns by 5. How I am calling the positive and the negative sequence? Let me explain that. The fundamental currents and voltages will be given by, let us take fundamental current, Im sin omega t. I am taking positive sequence, Im sin omega t minus 120, Im sin omega t plus 120. Now if we talk about fifth harmonic, Ia5 will be Im5 sin 5 omega t. Ib5 will be Im5 sin 5 omega t minus 600. So 5 omega t minus 600 is 5 omega t minus 240. Why? It is 360 plus 240. It is same as plus 120. IC5 will be Im5 sin 5 omega t plus 600. Plus 600 is 720 minus 120. Im5 sin 5 omega t minus 120. So if you see, B has the term plus 120, C has the term minus 120. That is the phase sequence is now ACB. That is how it acts as a negative sequence. Similarly, we can derive that the seventh harmonic behaves as a positive sequence. Now what will happen is, since the torque slip characteristics are for the fifth harmonic acts as negative sequence, the rotating magnetic field will rotate in a direction opposite to the fundamental. And we know the rotor has a tendency to follow the stator magnetic field. If the magnetic field is rotating in the opposite direction, it will produce a torque in the opposite direction, or we can say it will produce a negative torque. So what happens? This is the torque slip characteristics of the fundamental. Okay, this is the torque slip characteristics of seventh harmonic. This speed here is ns by 7. And if you see, the torque slip characteristic of fifth harmonic is reversed because it is a negative sequence field. So this speed here is ns by 5 in the negative direction. Now if we add these torques, what happens is the net torques look something like this. So there is this saddle region formed. This is called as saddle region. Now when we studied about induction motor stability, the condition that we took is dTL by dN should be greater than dTE by dN. Now suppose load torque is constant. If we take load torque as constant, dTL by dN will be 0. So the condition for stability will become dTE by dN is less than 0, that is negative. So here we have two places where the slope of torque slip characteristics is negative. One is this region where the torque slip characteristic has a negative slope, other is this. So we have two stable operating points, that is A and B. Now what happens if the starting torque is low? Then the motor will gradually build up its speed. So if it is stuck in the saddle region, that is also a stable operating point, then it will run at a low speed, because here the speed is less as compared to point B. That is called as crawling. Because it is running at a slow speed, we will say that the motor is crawling. Crawling means moving very slowly. So that is why what happens when the motor crawls. Okay, so crawling is nothing but running at low speed. Why it is running at low speed? Because it has a new stable operating point which has a lower speed. So what happens if it crawls? NR is less, due to which slip will be high. Now if we find out rotor current, it is E2 by under root R2 by S square plus X2 square. If slip increases, the rotor impedance decreases. If the rotor impedance goes down, rotor current increases. Rotor impedance goes down because R2 by S decreases. That means the rotor current is high if it is operating in the saddle region. If the rotor current is high, it can damage the winding. So it must not be allowed to continue to crawl for a longer period of time. Okay, so how to avoid crawling is, we will reduce or we will design the such winding such that there is no fifth and seventh harmonic. Okay, but crawling is less in case of wound rotor induction motor as compared to squirrel cage. Why? Because in wound rotor induction motor, starting torque is high, so it will accelerate faster, and if it accelerates faster, it will get out of the saddle region. Okay, but in squirrel cage induction motor, starting torque is low, so it will get stuck in the saddle region. So we will design the rotor such that fifth and the seventh harmonics are minimized so that the crawling is not observed. Okay, so it is a very dangerous condition in which induction motor runs at a slow speed and produces high rotor currents. Next term is called as cogging. Now see, there are teeth on both stator and the rotor. Why there are teeth? Because in the stator and rotor slots winding will be placed, so the other part will be called as teeth. This will be my stator design. This will be my rotor design. So here what I have done is, the teeth of stator and rotor are perfectly aligned. Okay, this is your slot where the winding will be placed. This is my teeth. Now as we know, like the current tries to take the path of minimum resistance, flux tries to take the path of minimum reluctance. Reluctance is given by L by mu A. So reluctance minimum means air gap is minimum between the stator and rotor. So now if you see, flux has got the path of minimum reluctance when the teeth are aligned. So if the rotor tries to move right or left, the reluctance of the path increases. So flux will oppose because it is getting the path of minimum reluctance. This is the most stable position. If you try to move the rotor left or right, then it will have a path of higher reluctance, which is an unstable position. That is why strong force will be produced, or it is called a strong alignment force, due to flux already getting a path of minimum reluctance. So that is why the rotor will not be able to move and motor will fail to start. This is called as cogging. It can only happen if the number of stator slots is equal to number of rotor slots, or it is multiple of the number of rotor slots. Okay, if both are multiple of each other or if they are equal, then cogging is observed. Okay, so one of the most popular method is skewed slots. Skewed slot means, what I will do is, I will tilt this slot by one slot pitch. So that way the flux will never attain a path of minimum reluctance. If it is never able to attain the path of minimum reluctance, then the rotor will rotate, because flux will always try to search the path of minimum reluctance, but it will never attain it. So it will keep on rotating. That way cogging will be removed. Okay. So by skewing, noise and vibrations are also reduced, cogging is reduced, and the torque slip characteristics are smoother. So that is how the cogging is defined and how to avoid the cogging. So let us summarize what we have learnt in this lecture. We first saw deep bar rotor, in which we saw the top layer had minimum leakage reactance, so that at the time of starting current was concentrated in top layer. But the area of cross section of top layer is less, so resistance is high. That way starting torque was increased. Similarly, we saw double cage rotor, in which outer cage had higher resistance and lesser leakage reactance, so that current at the time of starting flows through the outer cage and starting torque is increased. Then we studied about crawling, in which induction motor attains a stable position at a very slow speed, due to which slip is high and the rotor current is also high. Then we studied cogging, in which the rotor fails to start due to the strong alignment force between stator and rotor if the rotor teeth are multiple of the stator teeth or it is equal to stator teeth. So in crawling we were talking about belt harmonics, that is 6n plus minus 1 harmonic. We did not talk about triple N harmonics, that is 3n harmonics, because they do not produce any rotating magnetic field, so they do not produce any torque. Similar to belt harmonics, we can also talk about time harmonics. So remember, if the harmonics are present in the supply, those are called as time harmonics. Their synchronous speed is order of harmonic multiplied by synchronous speed of fundamental. So that is the difference between belt and the time harmonics. In belt harmonic, speed is synchronous speed divided by the order. In time harmonic, it is synchronous speed multiplied by the order. What is the time harmonic? It is a harmonic present in the supply voltage. So do take care of this fact when you are dealing with harmonic, whether it is time harmonic or a space harmonic. Okay, so this is all about your three-phase induction motor operation.